on to continuous. Now we're not going to spend a lot of time on continuous. We have talked about continuous random variables before, back in Chapter 2. So I will kind of discuss that at the end of the notes here, but we have done continuous random variables in some way. Now suppose we have a spinner here, and the spinner can go all the way, kind of starts here at 0. Here's 1/4, here's 1/2, here's 3/4, and then it goes back to 0. Okay, so it can stop anywhere. It could land on 0 technically, but when it wraps all the way back around, it can't really land on 1 because 1 is at the same spot as 0. Okay, so it can be equal to 0 but not equal to 1, even though they technically take up the same space on the spinner here. But it could land anywhere in between. So let's say right here, what specific value is this? It could be a fraction, it could be some infinite long decimal. Okay, so this isn't like this is clicking, like this is the Wheel of Fortune here, and we're saying it's got to land on exactly one of these spots. I'm saying there is infinitely many numbers here between 0 and 1. There's infinitely many numbers between 0 and 1/4, which seems kind of crazy. Okay, so how are we going to do probabilities? How are we going to write a probability distribution when there's infinitely many values here? And how are we going to tie a probability to each of those infinitely many outcomes? Well, once upon a time, we did the normal distribution. Well, I don't want to grab that. I want to grab... Interesting. Okay, I'm back. How can we assign probabilities, such as between 0.3 and 0.7? We're going to have to do this as areas, and we've done this before. Okay, so this shouldn't be a new idea here. Get that one back up. As in the case of selecting a random digit, we would like all possible outcomes to be equally likely, but we cannot assign probabilities to each individual outcome of x, and then sum, because there are infinitely many possible values. Instead, we're going to do areas between particular values under a density curve. Any density curve had an area of exactly 1, just like the normal distribution had exactly 100% underneath it. Even if I go back to my uniform distribution, this is a density curve. The area of this, well, no, yeah, that should be 100%, yeah. The area underneath this curve is 100% total here. A continuous random variable takes all values in an interval of numbers. The probability distribution of x is described by a density curve. The probability of any event is the area under the density curve and above the values of x that make up the event. So here we are at the end. So the random number generator will spread its output uniformly across the entire interval from 0 to 1. So here is our uniform distribution again. We can have anywhere between 0 and 1. Oh, we're not doing the random number table. We're saying if we could come up with random values between 0 and 1 from our spinner. That's what I meant to say. That here's our density curve here. This is what's going to seem a little odd, but we'll explain some of it in here. If we want to find the probability that x, our outcome of our spinner, is in between and including 0.3 and 0.7, well, let's estimate right here, here's 0.3, and let's estimate right here, this is 0.7. And we want to find the area between 0.3 and 0.7, which is just a rectangle. Okay, so how much area is there between 0.3 and 0.7? There's 0.4. And how tall is this? This is 1. So 1 times 0.4, this has got an area of 0.4, and that is also the probability. Fix that. The probability that x is less than or equal to 0.5. Well, 0.5 is right in the middle, and we want to be less than or equal to it. So the area of that rectangle is just 0.5. It's 0.5 wide by 1. So this has got an area of half. That's 50% of your density curve. For 3, probability that x is going to be less than a half or x is going to be greater than or equal to 0.8. Now, these two events, being less than or equal to a half or greater than or equal to 0.8, those are disjoint events. There's going to be no overlap there. So here's 0.5 and less than. I'm going to approximate, here's 0.8 and greater than. Now we're going to talk about two different ways we can get the answer here. This is, the first part we already said was 0.5. The area of this part right here, well, how much space is there between 0.8 and 1? 0.2 times 1 is 0.2. So there's 0.7. Another thing we could have done is we know the whole thing is 100%. Well, there's only one part we don't want, and that's this piece right here. And it's from 0.5 to 0.8, which is a difference of 0.3 times 1. This has an area of 0.3. So we could have used the complement rule and said 100% minus this piece we don't want gives us the pieces we do want in the end. So this and this end up matching. The probability that x is less than 0.6. Now notice here, I just said less than and not less than or equal to. So if I estimate, here's, let's say 0.6, and I want to be less than it, well, what's this area going to be? And notice for number 5, we'll kind of combine these two together here. Being less than 0.6 or less than or equal to 0.6. Well, how much area does 0.6 itself have? Here's what you need to think about. Imagine you've got a rectangle, a very, very skinny rectangle. And it's got a height of 1 because that's what this says over here. But what is its width? The width is basically nothing. 0.6 does not have any width to it. Okay? We're basically talking about a one-dimensional line here. It has length, but no width. So it has an area of, if you said nothing times 1, that would give you an area of nothing. So does it really matter if this says less than or equal to 0.6? No, it really doesn't. Because we were saying before that we're going to be finding the areas between things. And if we want to include a specific number will have a probability of 0. Okay, because it's basically a non-existent rectangle. So this is going to be 0.6, because that's going to be the area here. This will also be 0.6, because the or equal to makes no difference in this case. And then for 6, we kind of mentioned here, the probability that x is equal to exactly 0.8. What's the probability that we would get exactly 0.8 on that spinner? Well, essentially, it's 0. Okay, it's basically impossible to spin a 0.8 when there's infinitely many numbers that you could come up with. So some last observations here. The probability model for a continuous random variable assigns probabilities to intervals of incomes rather than to individual outcomes. Because we just mentioned, for as in part 2, all continuous probability distributions assign probability 0 to individual outcomes, like we saw here in number 6. Only intervals have values of positive probability, and when working with continuous random variables, we could ignore the distinction between less than and less than or equal to, because again, the or equal to is really nothing in the end. And again, we have worked with the normal distribution before. which is a kind of continuous distribution, a continuous random variable. And that's what we would do, for instance, if we had a normal curve and we said, if we want to find how much space, what's the area underneath a particular value, that's what we were doing. We were saying, normal CDF, our lower bound was negative infinity, our upper bound was whatever this specific number is, let's say it was -2 for a z-score, and that answer would give us the area underneath the curve from here to here, which is also the probability. The probability and the area represent the same thing. Well, I hope you guys have a good Thanksgiving. I really hope you watch the video so that we can start things. You have this last chapter before semester break. Many of you kind of need to maintain your grade, or you're pretty close to either bumping down or bumping up a grade. So we really need to make sure everyone's on board so we can get a good grade on this test and you can end up with the grade that you want to keep.